Okay, so let us continue our discussion. We are in week 5 and this is our lecture 2. So, strain analysis, right? And before we discuss today's topic, let us quickly review what we have done yet. So, we considered body and that actually deforms so what we did is line say PQ and that shifts to a new location say P prime Q prime. Now, we defined the displacement field as Ux, Uy and Uz. And the moment we define displacement field in terms of Ux, Uy, Uz, which are function of x, y, z, then we have the strain components. In 3D, we have 3 axial strains, and then we also have shear strains, right. In case of shear strains, we have to consider 2 components at a time and then accordingly we can find out the shear strains in xy, then yz and then finally zx, right. Okay, so these are the strain components and we also defined a matrix and it is called the displacement gradient matrix, right. So, if you have a displacement field, so first we find out displacement gradient matrix and then using the elements of this matrix actually we can represent strains. Now, if you look at this expression, we can easily conclude that gamma xy is equal to gamma yx, right. Similarly, for other 2 cases also we can easily show that, right. Now, we also derived the expression for complete expression for strains where we have the higher order components. So, the first one is again linear, what we have already written here, plus we have some higher order terms which I am not writing, you already have it. Similarly, for capital E YY and ZZ, and then finally also for shear terms capital E XY, we have identified the first part what we have here then so first part or the linear part plus the higher order terms, right. These are the expressions we derived in our last class. Not only that, we also quantified the strain that this line PQ experiences. So, it is E of PQ we have derived, and that is actually, let me write down epsilon, because we consider the linear variation only. So, we have epsilon x x n x square plus epsilon y y n y square plus epsilon z z n z square plus gamma x y n x n y plus gamma y z n y n z plus gamma z x n z n x. Okay. So, that is the expression for the strain the line PQ experiences. Now, you see in this problem we started with PQ, then we end up with P prime Q prime, right. For this PQ, we again define Nx as delta x by delta s, Ny is delta y by delta s, and Nz is equal to delta z by delta x, right. Now, the question is, we have another set of direction cosines Nx prime, Ny prime and Nz prime. So, if we consider say Nx prime, as per definition what we have here, we can easily sense. So, this is del x prime by del s prime. Similarly, N y prime is equal to del y prime by del s prime, and then N z prime is equal to del z prime divided by del s prime. Okay. So, we can also write del s prime is equal to the original length times 1 plus the extension, which is epsilon PQ, right. Now, if we wish to find out the expression for Nx prime, then we have delta x prime here, and in place of delta x prime we already know the expression. This is delta x plus delta u x. Refer our previous class note, we have already explained that, and then divided by delta s prime. Now, if we simplify this expression further, so what we have is delta s prime by delta s, and then within bracket we have delta x by delta s plus we have delta u x by delta s. Now, what is this quantity in the denominator? It is nothing but 1 by 1 plus epsilon PQ, right. Then within third bracket, the first term is again we can identify Nx plus, then we have this is basically the increment in delta u x over the length delta s, right. We know the expression, so we can easily write it down. So, it is This is again the expression we derived in the last class. You can refer our previous class note, right. So, we can simplify this. What we have here is 1 by 1 plus epsilon p q, and then within bracket we have 1 plus differential of u x with respect to x times n x plus so that is the expression for n x prime. Similarly, we can also derive the expression for n y prime. What will be that quantity? It is 1 by 1 plus epsilon p q within bracket plus we have u y differentiated with respect to z and then n z. Similarly, n z prime is 1 by 1 plus epsilon p q. Okay. So, now we have derived the expression for n x prime, n y prime and n z prime, right. And carefully look at the expression. It depends on the components of this displacement gradient matrix. So, the moment you find out displacement gradient matrix, then immediately we can quantify all these quantities. So, what we need n x, n y and n z plus the components of this displacement gradient matrix, and then immediately we can find out n x prime, then n y prime and n z prime, right. So, the strain problem in 3D is now quantified. So, we have defined all the strain components, plus we have also find out the direction cosines after the deformation, elastic deformation in this case, and we also considered linear strains. So, all our derivations are for linear strain. Okay. Now, 3D strain field is given by epsilon x x, epsilon y y and epsilon z z. Then we have gamma x y, gamma x z and then gamma y z. Now, one issue to be noted here is gamma x y is, we already have the expression, it is called engineering strain. And epsilon of x y is the true strain. So, engineering strain based on original dimension and true strain, it is based on actual dimension. And epsilon x y is nothing but half gamma x y. So, we can quantify either of them as and when it is necessary. So, now we can replace this strain field with epsilon also, Now, the question is there any plane? So, the question is there any plane that has only axial strains, and if so, what is that quantity? In case of stress, if you recall, we identified a plane where we have only normal stress, then that plane is called the principal plane. Here also we have normal strains and we have shear strain. So, you can also write it normal strain. So, if that is the case, what will be the strain field? Epsilon, 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 that is the strain field, and if that is the strain field, then obviously we can again use this strain field as our starting point, and we can find out what is the resultant strain. So, we can write in a similar way as we did in case of stress analysis. This is equal to, we have the new strain field defined by the normal strains only, because there will be no shear strain. That is the question we are going to answer. So, if that is the case, again we have similar eigenvalue problem here. And then again, as we did in case of stress analysis, we are not looking for any trivial solution which is n x equal to n y equal to n z equal to 0. So, for our case we will have the determinant of these matrix is equal to 0, right. This is equal to 0. And if we simplify this expression, again we will get a similar equation with 3 strain invariants this time. And then once we solve this equation, we will get 3 principal strains, epsilon 1, epsilon 2 and epsilon 3, right. And the 3 strain invariants in our case is, say, I 1 is equal to epsilon x x plus epsilon y y plus epsilon z z. Then I 2 is and then I3 is equal to the modulus of the 3D strain field, which is we have here. So, right. Then what we get is again the principal strains in case of 3D strain field. And for each of them, so we can consider each of them and then we can find out their respective orientation. So, we will have nx1, ny1, nz1, and then if we consider the second principal strain, we will have nx2, ny2, nz2, and the third one will give you nx3, ny3, nz3. So, these are the three sets of direction cosines that defines the plane for epsilon 1, epsilon 2 and epsilon 3. And as per our definition, you see there are no shear strains, and hence these are the planes where we will not get any shear strain. Now, for strain analysis also we can draw the Mohr circle, and from that Mohr circle we can again find out maximum shear strain. Now, if you look at the definition of the principal strain, these are the strains, they have no associated shear strains, but the plane where we will have maximum principal strain, again we will have some associated normal strain, right. If you draw the Mohr circle for this 3D strain field, you can easily find it out. We will solve some example in the next class and we will see how we can easily find out epsilon. We have ij, I not equal to j, then it becomes shear strain and maximum of that. So, max of this quantity. That we will solve some example using Mohr circle and we will find out, right. So, today we have learned how to start with this displacement gradient matrix, and then once we get the displacement gradient matrix, we can find out the new orientation of the line PQ and the components of the direction cosines nx prime, ny prime and nz prime that we have derived. We also derived the expression for principal strains epsilon 1, epsilon 2, epsilon 3 and corresponding direction cosines also we can easily find out the same way we did it for stress. If you recall, we need one additional equations the moment we consider say first principal strain and put it back in the original equation say here, then to find out the direction cosines we have to apply the properties of direction cosines, and that is nx square plus ny square plus nz square is equal to 1. So, we will consider two equations from this expression and then additional equation will come from the property of the direction cosine, and if we consider these three equations and solve for nx1, ny1, nz1, we can easily find it out. Similarly, we can repeat the exercise for other two principal strains. That we will do in the next class. So, with that let us close here. Please go through these derivations. Tomorrow we will actually solve some example and then we will see how we can solve the strain problem when we are given a displacement field ux, uy, uz, and then once we solve the displacement field and find out displacement gradient matrix, we can easily find out the principal strains. That will continue in the next class. Thank you very much.